Thank you, Lev. Thank you for this conference. Great occasion. So I just want to just comment on Tim's talk, which I thought was great, and I found myself agreeing with almost every single word. This is about the second time this has happened, Tim. I'm getting a bit worried about it. But except for, there was one snippet which I definitely did not agree with, which is the question of whether the quantum state could be a local beable in Bell's sense. Look, I do want to say a bit of history. So I did have several conversations with John Bell about this, particularly at Erice. Tim, you were at Erice. And I recall very much his views then, and he wasn't pushing the flash ontology. But it's true that the local Beelbos paper was before then. Erice was 89, was it? Something like that. So I remember, well, Philip Pearl was asking him, Phil was a bit worried about the tails, and Harvey reminded me of this recently. Bell's reply is, oh, don't be a ninny. It's typical John Bell, really. And he wasn't really worried about tails, I think, particularly, but I think maybe he was worried about structured tails, and I think that the appeal of the flash ontology is to get rid of the structure in the tails, which I can well understand. That's a different kind of consideration. Anyway, quick jump now. So I take that Tim is giving a challenge, really, on the basis of scientific method, and what is good scientific method, and I'm totally with him on that. And I would just like to say a paradigm that was set for all of physics was what Newton did in Principia. And what Newton did was, without a substantial theory of substance, without really knowing what substance is, without really knowing what mass is, certainly on the metaphysical side, a great deal of dispute going on at the time, Cartesians and so forth. Leibniz was on the scene. But Newton carefully refrained from any real analysis of what is matter. But he nevertheless could give an analysis of how matter moves in space in a way which is both intelligible and observable. But he only did it for certain kinds of matter. He did it for matter that is really clumped up and in a hard vacuum and free of other interactions, a relatively simple system. Had he to deal with something like the, chaotic motions in gravitational fields, he'd have got nowhere and did not have the tools to get anywhere with that. So, fine. What I want to suggest is that ontology and the Everett interpretation can be approached most directly and most simply in exactly the same way as Newton did. So, whereas for Newton it was certain kinds of matter, namely enormous numbers, very, very large masses clumped up, what works as a starting point in the Everett interpretation is, I'm going to idealize, but I can very quickly remove the idealization if challenged. So I'll idealize to the idea of a structureless particle which is extremely massive. Okay, you want me to remove the idealization. It's going to be a bound state of very large numbers of particles, but the center of mass degrees of freedom are going to decouple, and I'm just going to look at the center of mass degrees of freedom and the wave function for the center of mass degree of freedom. And I'll start off just with a single such particle, the wave function for its center of mass, and suppose it's sharply peaked. It's a wave packet, a coherent state. I have it written, I should perhaps do with a pointer. Oops. I don't want to do slide, I was worried I'd do that. Where's the, is there a laser? Can I just want to point at the, oh, I see. Oh, okay, yeah, I can do that. So here is just a wave packet, I'm just defining it. QP are parameters which define this wave packet, namely that it's centered at Q and it moves with momentum P. And because it's massive, it doesn't, there's not much wave packet spreading. I mean, it's really totally negligible. A gram of matter will stay localized to within a millimeter for millions of years if it's just the free Hamiltonian acting. So there's no wave packet spreading here. And now I just ask, let's suppose that this wave packet is, oh, see, I've got a curious spelling of wave packet up there, haven't I? Sorry. So now let's suppose this wave packet is coupling to an external potential. Okay, so on the left-hand side, I've got some equations. I'll come back to it. On the right-hand side, I've got Ehrenfest's theorem. We all know and love Ehrenfest's theorem. Normally, of course, it's interpreted in terms of probability. But when you've got a very sharply peaked wave packet, and if you're looking at the expectation value of some function with respect to that sharply peaked wave packet, so that would be, on the left-hand side, something like this. So here the function in question is the expectation value of the position. So I've just got x as the representation of the position operator, x multiplicatively. So this thing, this expectation value, is just q. That goes back to the definition of what a coherent state is. But now look at any function of the position operator in a sharply peaked state. And just as a piece of mathematics, it equals f of q times what is effectively 1, approximately 1, so it just equals f of q. So the expectation value of a function f of q, nothing to do with probabilities, I'm just looking at the integral of these quantities, is this function f of q. Now, take f of q to be the derivative of the potential operator. So now the equation's on the right-hand side from Ehrenfest's theorem, and given sharply peaked in both position and momentum space, we can deduce that the parameter p that I started off with, and the parameter q over here, which remember are just the parameters that label the coherent state. So these parameters change in time in accordance with elementary classical equation. So we can get a bump, something sharply peaked, well-defined motion, doesn't spread in time, and it's just moving about under the influence of this external potential. And that seems to me entirely intelligible, even though I don't have a good account of, well, what does it really mean, this bump? Because, as with Newton, I do not have a developed metaphysics of substance. Now, I think what makes this particularly interesting is if you go over to the interacting Coulomb potential or gravitational potential, even better, go over to the interacting case, where now the potential that I'm looking at, the potential function, is a function of several different degrees of freedom. And exactly this analysis goes through. You'll have several bumps in a product state, and as long as the gradient of the potential is approximately constant over the widths, these bumps will all move around executing gravitational motions. So in a sense, the very first and clear model of ontology that one arrives at in the Everett interpretation is pretty well what Newton had. It is a Newtonian gravitational collection of masses gravitating and moving around executing classical motions. And that seems to me intelligible and entirely clear. And let me also add this, that Everett, in his 57 paper, spoke almost nothing about this, but in his long dissertation, so-called published in 73, his theory of the universal wave function, he did have this. He had this exactly, but spread over 3 pages, schematic, and right at the chapter 5, there were 6 chapters, chapter 5, which was supplementary topics. So I think poor Everett was very badly advised by John Wheeler. It should not have been in supplementary topics. It should not have been excised from the thesis. It was the thesis that was published as 8 pages in length. It should have been right in there, and it should have, I think Tim is making a very important point. It should have been right in there to say it's extremely important that we can extract something recognizable and intelligible as an ontology in 3-dimensional space. He did mention it in the 57 paper. He talked about a mechanical model of the machine that would do the Stern-Gerlach or whatever experiment you're interested in. And it was important to him that that machine be mechanical, and that then became clear in the supplementary topics in the long dissertation, because he analyzed it, or referred rather to von Neumann's analysis. And a lot of von Neumann's apparatus is needed to get this out. I know I'm speaking for too long, I'm sorry. Anyway, I just say this has not been appreciated in Everett's work. Right, sorry, thanks.